Okay, good morning. Homework is good? Still next time, right? Last time we discussed the fundamentals that will be used in this class. So including like decibel, amp hours, and information theory, the channel capacity. So any questions? Today we are going to discuss a new chapter, the analog modulation and the demodulation process. In today's class we are going to finish double sideband suppressed carrier modulation and demodulation, and also some simple circuit that can be used to implement this. We know when we transmit a signal, for example, right now I'm transmitting my voice to you, so you directly hear my voice. So this is called baseband transformation. That means the information from me does not need any transformation. I directly transmit, you directly receive this. So this is baseband transformation. Baseband transformation, the good thing is we do not need extra circuit. And the bad thing is, for example, we cannot transmit very far away, or for example, the capacity will be limited. There are some disadvantages. So today we are going to discuss carrier communication. That means we are going to use a signal called carrier, and we are going to discuss three. Okay, so this is a modulation. Modulation means the information will be embedded into another signal. So we do not directly transmit the baseband signal. Instead, we transmit the modulated signal. At the receiver, when you receive the modulated signal, for example, the AM signal, the received signal is like 1,000 megahertz, or at least several hundred megahertz. We cannot directly listen to it. We need to use a process called demodulation process, to bring back the signal, the modulated signal, back to its baseband signal. If we use this method to communicate, that is called carrier communication. The carrier signal, C, time domain signal, usually, for example, we use a sinusoid function. So we have A, amplitude times cosine, omega CT, C means carrier here, then plus a phase. This is a very typical sinusoid function. Now we see we have three variables that we can control here. The first one is this amplitude. The second one is the frequency. The next one is the phase. The phase, this one is only the initial phase. Means it is the phase when t equal to 0. So the phase is this part. So this is the phase. And this is the frequency. This is the amplitude. So for this carrier sinusoid function, we have three variables that we can control. Suppose we have a baseband signal MT, that is the information we want to transmit. Here, my voice, or so any video, or the internet signal, anything. This is the baseband signal. Baseband. If the information is embedded in here, that is called amplitude modulation. If this information is reflected in the frequency, then this is called frequency modulation. Then if this signal is in the phase, then this will be called phase modulated signal. So it's very straightforward. Today we are going to discuss this one only, and we have several schemes for this AM, but today we will only discuss the first one. It's called double sideband suppress the carrier. Right? So this is one of the 7. So how to implement this double sideband suppressed carrier in time domain? In time domain, we know the carrier equals A cosine omega CT plus theta. But for simplicity, we can assume the initial phase equal to 0, right? So we assume this zeta here equal to 0. So we just A times the cosine omega CT. Okay? So omega C is the frequency, omega CT is the phase, and A is the amplitude. So we said we want the baseband information to be in the amplitude. So the very straightforward way is we just change this A to a MT. Now the baseband information is in the amplitude. Yes, that is the time domain representation for double sideband suppressed carrier. So we are going to explain why it's called double sideband, why it's called suppressed carrier. So, but this one is the modulated signal. So we are going to represent this time domain signal with a phi and as a function of t. So phi t equals mt times cosine omega ct. So in time, you can see this modulation is very simple, right? The baseband information multiplied by the carrier signal. Sometimes you can see there's an A constant here multiplied by A, so that's fine. We can assume A is unit 1, so that's not a big deal. The key here is the amplitude, the baseband information multiplied by the carrier signal. So that is the time domain representation. Right? Now, let's see what does this look like in frequency domain. In frequency domain, we suppose this is in time. Suppose the MT must be has some spectrum, right? So the information transmitted has some spectrum. For example, my voice, that is like from DC up to less than 20K. That is a typical human being voice, from 0 to less than 20K. And if we take the Fourier transform, that is from 0 to maximum 20K here, if we use a frequency. If you use omega, then 20K times 2 times pi, right? But mathematically, usually we said this one will be symmetric, so this is negative 20K here, right? So in real life, we do not have any negative frequency. So for example, in the lab, right, if you observe this signal with the oscilloscope spectrum analyzer, you can only see this part. You cannot see this, the whole thing, because there's no such thing as negative frequency in real life. This is only for mathematical simplification. So this one will be symmetric. So the power, you just flip this part, add it to this one. That's all. So this is a time domain signal. Time domain signal, for example, here, this MT can be like this is in time. And this one is the waveform in frequency. So cosine omega CT, we know this. Cosine omega CT, we know this is a singular frequency. So the omega C will be this one 20K times 2 pi. This negative 20K times 2 pi. Right? So this is omega. And this one is also omega. So the omega C will be somewhere here. So this is a singular frequency. Now we multiply these two in time domain. If you still recall Laplace transform, Fourier transform, then the spectrum of this signal, modulated signal, will be this signal exactly, but shifted to here, and also negative omega C, then reduce the amplitude to half. Right? So that means the modulated signal will be like this. This is omega C, this one is negative omega C, and we shift this one to here and reduce the amplitude. For example, this one is A here, then this one will be like this. This one will be half A. And we have another copy shifted to centered at this point. Right? So this one is still negative half A, like that. So you can see the information, the spectrum information here will be copied to be centered at omega C plus omega C and minus omega C. Right? The amplitude will, this is A, this is half A, this is half A, so they still have the same amplitude. Right? Now, we do not have this information anymore. This information, this signal here is gone. It's not here. Right? How to get this? Just the Fourier transform of this multiplication. If you still remember in the table, that is a capital M, this one is a capital M omega. Right? And so that's why it will be capital M omega plus omega C. This one will be capital M omega minus omega C. Centered at positive omega C. This plus omega C will be centered at negative omega C. And the amplitude will be equals half here, and this one also equals half here. Okay, now let's summarize. What is the time domain? What is the AM modulation here? If we look at AM process in time, what is it? It is just a multiplier. You use the baseband information and multiply by your carrier signal. That's it. As simple as this. Any questions? So in time domain, just your baseband information you want to transmit, multiply by the carrier signal. That is in time. In frequency, this is the information you want to transmit. You just shift this frequency to a higher frequency. This one is still higher, right? This negative omega C is still very high because this one is exactly the same as this one. So you just shift your baseband information frequency to a higher frequency, centered at the carrier signal. Usually, in practice, this omega C will be much larger than the highest frequency here. For example, again, in the AM radio, the voice is 20K. This one can be like, for example, channel 950 kilohertz or 1000.6 megahertz up to that one. So anyways, it's much larger than this one. Usually, for example, 20 times or up to 100 times larger than this one. There's a reason for this we are going to discuss later time. Okay, any question? Okay, anyone can repeat? How do you see the modulation in time? What exactly? I ask you to explain modulation process. You tell me what is it in time domain. I'll give you a time domain signal, okay, my voice like this. I'll give you a sinusoidal function. What is the modulation process? What is it? You need to only tell me one word. Multiplication. And that's perfect. Now, how do you look at it in frequency? So for example, I'll give you some frequencies. Frequency, that is the information for the baseband. How do you modulate this spectrum? How do you see this in frequency domain? Don't talk about time, only frequency. Shifting. You shift your frequency to a higher frequency, that's all. Our voice is from 0 to 20. Now, if you listen to 950K, you shift your voice from 0 to 20K all the way to be centered at 950. So, very simple, right? Okay, now suppose this is a modulated signal. Okay, let me draw the time. So this one is the spectrum. In the time, suppose MT looks like, I will look at this. Suppose the time looks like this. So that is MT. Just make an arbitrary assumption. Then we use this one to multiply by this cosine function. As we said, the cosine function, the frequency is very high compared to this one. So it will look like this. It's not good, the sinusoid function, but you know what I mean, right? This is just the sinusoid function. So this one multiplied by this in time. So what we have is, now for this one, carrier, the amplitude is a constant A. Or just say constant 1, if we scale this one to 1. Now this one multiplied by this, what we have is, we still have this sinusoid function. Right? We still have this sinusoid function, but the amplitude is no longer a constant 1. It is ft. So what we have here is, we are going to copy this baseband signal. That is our amplitude. Now inside, we are going to have like, this one is here. We are going to have this, the amplitude will be changed from 1 to empty. So we still have a sinusoid function, but the amplitude is no longer constant, it is empty. So if we observe this modulated signal on the oscilloscope, that is what we have. Any questions? In 315, you are going to do this in the lab. So in this class, we don't. So we will focus on digital. So this part, you can only start from the lecture notes. Any question on that? Okay, now we said this, the name is called double sideband. Why we call this double sideband? Alright, look at this. The bandwidth here equals 20K, right? From 0 to 20K. But mathematically we have it from negative 20 to this one. So now look at this one. We shift this, the whole thing to this side, to the right hand side, centered at omega c. What is the frequency here? So omega c plus, suppose this one is the bandwidth, so the bandwidth is B Hertz, right? Converted into radians per second, that will be 2 pi times B. And this one will be negative 2 pi times B. So this one here will be omega c plus 2 pi times B. And this point will be omega c minus 2 pi times B. Now look at the bandwidth of this thing. This bandwidth here is from this point to this point. And this copy is exactly the same as this one. So we can just ignore this. The power are added together. So what is the bandwidth of this modulated signal? It's from omega c plus 2 pi b to omega c minus 2 pi b. So we subtract these two, the difference is 4 pi times b. So the bandwidth will be equals 4 pi times b in radians per second. So we divided by 2 pi, that gives us 2. So the original bandwidth for the baseband is b. Now we have 2b. What does that mean? Called double sideband. The bandwidth is double. Does it make sense? Alright? So the modulated signal has double sideband. The bandwidth is double. Why is called suppressed carrier? This one. Look at this one. In time domain, we multiply this signal with this. So we do have this frequency here, singular frequency. But after the multiplication, do we still have this information here? No, it's not here. This information is totally this baseband information. We do not have any frequency from the carrier. For example, the carrier equals 100, suppose very large. See, we don't have this information. We only have this copy, just shift this one to be centered at omega c or negative omega c. We don't have this omega c and negative omega c. This is the impulse, right? We don't have this impulse information at this point. So that's why it's called suppressed carrier. So the carrier signal is gone. We only have the baseband information, but at a higher frequency. So that's why we get this name. Double sideband suppressed carrier. Suppressed carrier, that means that sometimes we can't have the carrier. Okay, yes, we are going to discuss that next time. And in this time, we don't. So there's no carrier. Any questions on this? Okay, so suppose you have your voice baseband MT, you modulate this. That means in time you just multiply with the cosine function. In frequency you say, okay, I shift my frequency to a higher frequency band. Okay, that's perfect. Then at the receiver, you are going to receive the time domain signal like this, or you are going to receive the frequency domain signal look like this. They are the same thing, right? These two are the same. For the same signal, you just look at it in time, it looks like this. If you look at it in frequency, it looks like this. Everybody understand this, right? They are the same thing. Both are the same. Like this. This one is a cosine function here, right? This is on the oscilloscope. You're familiar with this. Now this is on the spectrum analyzer. That means you look at this only with the RF frequency, because we know there's only single frequency here, so this is only this one. Question?
So with the frequency, why is the amplitude half of the carrier signal?
This one?
Yes.
Because we have two copies. Oh. So we add up together, that's the other one. Okay. Good observation, right? So mathematically it will be this, change into half m omega minus omega c, then plus half capital M plus minus n plus omega c. So we have half here, so this is 1 here. Yeah. And we have two copies. Now we receive this signal. Suppose this is the voice, or music and your FM music on the AM radio. Can you listen to this? Right? Our ears cannot.
Well, I mean, you could, but probably wouldn't.
Have you ever tried, when you study, for example, AC circuit, have you tried to listen to a 1 kHz like signal from the signal generator? You can hear, right? How about the 2K, 10K, 20K, 30K? Okay, 30K is beyond the ability of our ear, so we cannot listen to 30K, let alone this 950K. You cannot hear. This is like a supersonic or something. Only maybe the bat or something else can listen to, or dolphins. Human beings cannot. So that means if you my ear is here, right? The AM signal is in the air, right? Can you hear anything? No, you cannot. Right? Surprise? Can you hear the AM radio? The FM radio? No.
Right.
Why you say, oh, the signal is too low? Yes, that is why. Even you amplify this, you still cannot hear this because the frequency is outside our bandwidth. Right? So as the receiver, if you want this signal, you need to get this one, not this. This is what you receive. You receive this, this is what you want. Or in frequency domain, you receive this one here, but what you want is this one. This is what we want. This is what we want, not this one. So we need to do something at the receiver side. Once you receive this in time, or receive this in frequency, how to bring this back to here, or how to get this from here. That process is called demodulation.
Called what? What is it called?
Demodulation.
Oh, demodulation. I didn't know what you were saying.
Demodulation here. From transmitter to receiver, that is called modulation. Now, at the receiver, you want to get the original baseband signal. This is called demodulation. Add up together, combine together, is called a modem, right? So at the beginning, you have a modem at home. So do this modulation and demodulation process. These two can combine together. And actually, these two are the same thing. There's only one little difference. Okay, let's see how to get this one. This one is not that straightforward, but we are going to start from math. I will erase this one. The received signal, double sideband suppressed carrier time, that equals mt times cosine omega CT. That is the transmitted and also our received. So our received, I'm going to multiply this signal with cosine omega CT. What is this? That is the carrier signal at the transmitter. So suppose I know this one. I will use this one again at the receiver. So at the receiver side, I will multiply by the received modulated signal with this carrier again. Does it make sense?
So
I received this one, right? This is at the transmitter. You multiply this baseband signal with your carrier and you transmit with the cable or wirelessly, no matter what. You transmit this. That's your work is done. At the receiver, you receive this one, right? Okay, what we need to do at the receiver side is once I receive this, I multiply with the carrier signal again. It is clear. You know what we are doing, right? You multiply this again. Okay, now from math, let's see what happened. So this one we know is this, so mt times cosine omega square omega t, cosine omega t again. So that is cosine square omega t. Now this trigonometry, so cosine squared equals half 1 plus cosine 2 omega ct. Now this one will be equals mt over 2, then plus mt over 2 times cosine 2 omega ct. So this is our received signal multiplied by the carrier signal. That is what we have. Now let's recall what we want at the receiver. We want the original baseband signal, which is mt. But what we have is here half mt. Oh, that is okay, right? So we just multiply by 2. That is only the amplitude, the power. So that's fine. The information is still here. So that is what we want. What is this one? Look at this. mt times cosine 2 omega ct. What this signal is? This is also a modulated signal, right? The frequency is 2 omega c instead of this one. Look at this. You compare this with this one. What's the difference? This is a modulated signal at omega c. This is also a modulated signal, but at 2 omega c. So that means the spectrum of this will be shifted even further to the right, double 2 omega c. So that means the frequency is even higher. We cannot, maybe even the dolphin cannot hear this anymore. How about this one? Oh, this one is good. This one is our baseband signal. That is what we want. So if we have any way that we can separate these two, because in time these two are combined together, right? If we can separate these two, then we are done. This is what we want. So how to separate these two?
divide.
Divide. This is the process of demodulating. Okay, now look at this one. The spectrum of this is this one, right? But only half of the amplitude. So this one will be, I will plot at this point. We know the spectrum of this one will be here. So look at this. This spectrum will be just centered at here. So this is half F. And this one here will be centered at 2 omega c, and this one is negative 2 omega c, even less, a quarter. These two are combined together. Right? That means this one is here, like this one. So how to separate this? This one is what we want. This and this are not what we want. How to separate this? Can we use a filter to do this? This is what we want. This is 0. This is 2 pi times b. This is 2 omega c. This is centered at negative 2 omega c. We said this one's frequency is very, very high compared to this one, so these are separate. So we can use a low pass filter to cut off this part, to cut off this part, and have this part only. So followed by this multiplication, we use a low pass filter. We have what we want. Any questions? So at the receiver, what we need to do is you multiply by your received modulated signal with the carrier signal again, then followed by a low pass filter. We get what we want. That is the explanation in time domain of the demodulation process. Questions? Okay, now let's look at how to explain this in frequency. Right? Look at this. This one is the received signal, right? We multiply by this again. We call this demodulation. Can we call this modulation? We call this demodulation, no problem, perfect. My question is, can we call this also a modulation process? What is a modulation process? You have your signal, baseband signal, multiplied by a carrier, multiplied by cosine function. Are we doing this at this receiver also? Yeah. See, you have this signal, although it's not a baseband, but it is a signal. Then you multiply by cosine. So that means you are still doing the modulation process in time. So that means in frequency, we are going to shift your spectrum to a higher frequency, right? That means you are going to shift the spectrum of this to a higher frequency. Okay, now look at this. What is the spectrum of this? It is look like this. Make sense? That is what we already know. So the double sideband suppressed carrier spectrum looks like this. So that is at the receiver. You multiply this cosine, that means we shift this spectrum to the higher and to the higher frequency, centered at omega c and negative omega c. What is the center of this spectrum? 0. It's here, right? Because they are two are symmetric, so the center is 0. Now, this modulation process shifts this spectrum to be centered at omega c and negative omega c. So what we do is we shift this total thing to the right, move this 0 to omega c. So what do we have here? This is 0, this is omega c. So we shift this 0 to here. Then, where is this? This one will be 2 omega c, right? Where is this?
0.
0, right? It will be like here. This amplitude equals half. And keep in mind, when we shift, we need to reduce the amplitude to half because we have 2 copies. So now we have 2 copies. So what's the amplitude here?
1/2.
It's a quarter, right? Right? How about this one? Also a quarter, from half to quarter. So go ahead.
Every time you shift, you divide it by 2 again?
Yes.
Every time?
Yes.
So if you shift over again,
You shift it to the right and to the left because you get 2 copies. Right? So this one is only shifted to the right.
So what if you shift that one to the left?
This signal, you shift to the right and to the left. Then you reduce to half each. Because this one is 1 here. You need to shift on both sides mathematically. So you need to reduce the amplitude to half at the same time. It's just like a copy. You have one copy here, now you have two copies. The amplitude of each must be reduced.
But you still only got 2 copies when you shift it up there.
Yeah, you have two copies. Each one is
When
half.
you shift right there to 1/4, you still got 2 copies. So why you go down again?
This one is only one copy of this.
Oh,
So
it's one
this
copy.
one here,
Then-
this-
oh, I thought you were shifting.
This
both.
big
You
thing
shift-
is one copy shifted to the right,
Okay.
centered from 0 to omega c. So the amplitude will be reduced from half to a quarter.
So it's really like we're only moving that one.
Yeah, we only move this one to the
No,
right.
you moving that one right there at one. You're not
This
moving
and
that.
this are together. They are grouped.
No, it's that one signal right there.
This one.
Yeah, you
Yeah,
only moving that.
I move this one from here, right? This one is here.
Yeah.
Look at this one. From here to the right,
I
reduce
know.
to half.
Then you
Then
move it
to the
down.
left. Then to the left.
You get what I'm saying? You're not moving that. You moving that.
Yeah, move this, yeah.
Yeah, you're not moving that.
It's just a mirror of.
Yeah, that's just a mirror. Yeah, pretty much.
You shift this is frequency is 0.
Yeah,
I shift this one to the higher frequency,
yeah.
reduce the amplitude by half to
Yeah.
half. And you need to do this to the left also, same time. So negative omega c, from 0 to negative omega c, also reduce to half.
Yeah.
So something like you copy this one, you get two copies, and each copy is reduced to half amplitude. Make sense? So that one is easy to consider. This one, shift to the right and to the left, reduce the amplitude. Now this one is maybe a little bit not that straightforward. Why? Because this two is the combination, is our information. In this case, here, modulation percent, this one is our information. We have only this one. So we have two copies. Now for this one here, look at this one. This information is this and this. So now you consider these two as a team. And you need to move these two together to the right. So these two together from here, from centered at 0, then to the here, centered at omega c. Make sense? We have two parts, right? This part will be at 2 omega c. This part will be at 0. And this two only shifted to the right from here. And you reduce the amplitude from half to a quarter. But we still need to shift this one to the left at the same time, right? So shift is seen, the team to the left, centered at negative omega c. So this one will be at negative omega c, so will be here. But we have two of these portions. This one will be at where? Shift this whole thing to the left by omega c. So this one will be at 0, right? Alright, so this one is 0, so it will be like another quarter. So quarter plus quarter, because these two are exactly the same. So quarter plus quarter equals half. So this here is a quarter, this one here is a half. Are you done? Not yet, we still have this one. These two are team. You only shift this one to here, this one also needs to have, right?
So you want to the left.
So we have this one at a negative 2 omega c, right? Like this one. And this amplitude equals a quarter. Perfect. So we shift this one to the right and to the left. That is what we have. Now look at this. What is this? This is the baseband information, because all these are the same, so add up together still the same. So this one is the MT. So this one is M omega. But the difference is this amplitude equals only half. Not as here equals 1. But we don't care that, right? You have a lot of amplifiers. You can boost this one to 1 to 10. That's no big deal. This one equals a half. This one equals a quarter. So that will be M omega plus 2 omega c. And this one will be a quarter M omega
Minus.
this one will be minus.
Yeah.
Right? This one will be plus 2 omega c. Right? So that is the spectrum of the received signal multiplied by cosine omega CT.
How that won't be minus and that won't be plus? For the shift.
Oh, to make it go back to zero?
If you have a signal, okay, for example,
Oh, okay.
ft, right? From here to here, t minus t0, that means you shift this waveform to the right by
Yeah.
t. If you get t plus t0, that means you shift this parameter to the left by t0, right?
So both of them shifted right then? Or they shifted left?
This both
Shifted to the right?
to the right, and this both to the left.
So both of them should be plus then?
Yeah, because these two are a group. These two together is the spectrum of this.
So why you got minus on this side then?
Which one?
At the top?
Which one minus?
Oh, yeah, right.
This one?
No,
On the right side.
The right side.
Right, so this minus because this is 2 plus c. We shift this one to the right at 2 omega c, so that is plus 2 omega c, so this one is minus 2 omega c.
What's the point of copying it on both sides if you can just get the original signal from one side? Is it like a result of something?
Okay, that's a very good question. Okay? His question is, if we shift only one, so we get this one. So we already have this one, although it's just a quarter, right? Alright, that is called single side band. Alright, so we are going to discuss this later time. But right now, you're going to use double side band. Alright? This is the next topic.
I mean, it seems like it's
Yeah, this is two. See, we always emphasize, okay, these two are exactly copied. Exact. Why you want to need two?
it
So we can use only one.
It seems like it's a result of something. Like,
Result something is, okay, so the key here is we don't have this information here. So that's this is the point for suppressed carry. So you don't need the transmission this one here. Right? And also it's easy to demodulate. For you said if you only transmit half, later time next time we are going to discuss the circuit will be much more difficult. So you are going to spend more on the circuit, on the implementation, but you see what spectrum, that is also very expensive. So it depends on you. And this one here, we waste some spectrum resources, but the circuit is very simple. So you need to balance it.
Yeah.
That's a very good question. Yes,
Yeah.
that is how we invented different schemes. And you think, oh, why I need two copies? I can only use one. Upper side band or lower side band. That is exactly what we are going to discuss next time. Yes.
Bruh, if you got one, right, you see where it is at one. How you get zero is 1/2. If zero supposed to be one.
Which one?
If you shifting it, how you get 1/2 at one? You see right here you got zero. That's at one.
Which one? From here?
No, right here, this
On the
first one,
left side.
the original signal right there.
This one?
Yeah, at zero is equal to one, right?
Yeah, that's 8.
Okay, how did you get zero is equal to 1/2 right there?
This one?
Yeah.
Okay. This one you get a half and half, right?
Yep, they go on two sides, right?
Yeah, so each one is half. Half plus half equals 1. No big deal, right?
Yeah.
Okay, now you shift this one to the right, you need to divide it by 2, right?
So 1/4.
So this one will be 1/4 here. This one will move to here, and you have 1/4.
Oh, both of them go both ways to the middle, that's you saying? And it equal 1/2?
This 2 is the family, is the group.
So when that one go over there, that one go over there.
No, these 2 need to move together.
I know what I'm saying, but that one gonna be there and that one gonna go right there.
so you have
You hear what I'm saying?
This one will be here. This one will be here.
I know, then you gonna go the other way, right?
And all the way, this one
Yeah, you shift
will
back.
be here. This one will be here.
So both of them going to the middle.
This one,
So he's saying, how does it meet in the middle to be
That's what I'm
1/2?
saying. You going
okay.
both of them going to
The key here, this one is exactly equal to this.
Right.
So this one here, a quarter. This one is a quarter of this,
Oh, okay.
right? And a quarter of this goes to here. So this 2 quarter of quarter. So the quarter of the same thing. So that is a half. So that's why we always say these 2 must be exact copy. If otherwise, you're going to mess up at the center. So these 2 must be same.
I got you. That makes sense.
Alright?
So if you want to shift again, you gotta go to a fold, make it see on both sides.
Yeah, so that's what we focus on. Okay, in frequency, you shift to the right and to the left. and reduce to half. That's always like this. Right? So now the group is this one. So we have two. You shift this two to the right, then shift this two to the left. Right? This one to the right, centered here, reduce from half to quarter. And this one from half to quarter. So that's a quarter here. Then you shift this one to the left. This one will be here, a quarter. This one will be here, a quarter again. But look at this one. The first quarter is this. The second quarter is this. They are two of the same. So that's why quarter plus quarter of the same thing equals half. This one. Yes?
So what device will make it shift like this? For the what device will make the signal shift like this?
That is also a good question. I will ask you. What device can make this shift? Okay, the device we want to implement in lab is on time, right? In time domain. You can only do this in time. We human beings live in time, right? So you can only do this in time. And we always focus on this is how you see this in time, this is how you see in frequency. We are discussing here in frequency, shift this, shift that, on the left and right. All this translated in time is what?
Multiplication.
Multiplication. So if you have a multiplier,
Okay.
then you do this.
So it shift.
So a multiplier can make you manipulate any frequency.
Frequency shift.
Okay.
So when you really do this, implement, that is our next topic today, right? Implement this. So you just multiply, that's all. So very simple. But how to understand this in frequency, you shift the frequency. You do not actually move this frequency shift. You cannot do that, right? You need to multiply in time. Okay, any questions on this?
Can you go over how to get the original signal from the transmitted signal again?
Okay, this at the transmitter you do this time this, right? That's modulation. And at the receiver you receive this one, right? So that is this part. I see it. It's actually the same thing. You need to do an extra step. You multiply by this cosine omega c again. This is what the receiver needs to do. That is in time. You say how to do this in time? Yeah, you receive your signal, you multiply. You have multiplier. You multiply this signal. Okay. You may ask, how do I get this signal? Okay, so in labs we directly steal this from the transmitter. Right? You do the transmitter here, you do the receiver here. You just signal directly connected this one. In the lab, we said we steal the signal. In real life, I transmit here in Mississippi. I know this is my signal. You receive this in California. How do you know you cannot steal my signal here? You need to generate locally. Right? So that is another technical problem how to do this, but we don't discuss the details.
So that's low frequency, not high frequency.
This is high frequency.
That's high frequency?
Yeah, that's omega c is always the same. This frequency is much higher than this 20K.
Okay.
Right? So you receive a signal, you multiply by your carrier signal again. Then you pass through a low pass filter, you get what you want. That is how we explain this in time. You may ask, why? Why you multiply this, you use a low pass filter, you get what you want. How do I know that is correct? Alright, so mathematical proof. Right? You receive this signal, you multiply by this cosine, actually you have mt times the cosine squared, which equals this. All these are trigonometry, right? So equals this. Look at this. This one is what we want. This part, the spectrum of this part is even higher. So we use a low pass filter, we get this part. That is the mathematical proof, theoretical. So we know this is correct. I guarantee this is correct. So if you don't care this theory, you just want to do it, so you multiply by the carrier, you follow it by low pass filter. That's all.
That's it.
That's it. If you don't believe me, see, I can show this. That's all.
So what about the noise? It ain't gonna...
Where's noise? We didn't discuss any noise. Right? So in this class, we don't discuss any noise. So that is more complicated. So because this is only 2 hours and we need to discuss the digitals. This one, we don't discuss noise. Yes. Okay, any questions? So you need to know why it's called double sideband. Why it's called suppressed carrier. Eh?
Because you don't get some of the signal, you don't get the whole signal.
Yes, and you need to know how to look at this in time. For example, somebody asks you, what is modulation? How are you going to explain this? Okay, in time you just multiply by your baseband signal with a cosine function, that's it. As simple as this, you just multiply these two signals. You give me a multiplier, then I can do the modulation. Two signals multiply, that's all. What is the demodulation process? Oh, simple. You give me your received signal, I multiply by the same carrier signal again with another multiplier. Then I use a low pass filter at the end. Then I get the baseband signal. What I said here is the explanation in time. How to explain all these things in frequency? Right? So you have a baseband signal, that means you have a spectrum, right? Okay, if I can manage to shift this spectrum to the higher frequency, that is the modulation. Right? And I shift this one to even higher, one part and some part to the center, to the zero. Then I use low pass filter. I get this one here, low pass filter. Okay, then that is the baseband information. So that is a demodulator. So after we have done this, you need to use a low pass filter, right? To cut off this, to cut off this. This one we don't want because this one is even higher frequency. No one can hear this. We only need this one. So you need a low pass filter. Right? Now you may ask, why is that this frequency must be very, very higher than this one? Right? If it's not high enough, look at this. Right? If not high, this one is original, right? Right? Now you shift it to the center at omega c, we say that omega c is here. Like this, like this. If this one is not high enough, you only shift at this. Look at this one. This is what you have. If your omega c is small, this is B here, your omega c is small, come here, you shift only a little here. Then you shift this part to here, this part to here, this part to here. So you are going to see in the middle, you are going to mess up. That is called aliasing. You cannot use a low pass filter to get what we want because everything messed up to get messed up. So that's why this one must work. Why I said, okay, you may argue, okay, if this one is larger than this one, that's okay, we understand. But why I said we need this one to be large, greater than this one. Right? If this one is equal to this, what you have is, you are going to have like this. Now this is what we want, right? So you just use a low pass filter, get what we want. The question is, can you make a low pass filter like this? No, you can't. You cannot make a low pass filter as a perfect window. If you already done some filter design, the low pass filter usually looks like this. You have some like transition, right? So that means your filter can only be like this, or be like this. You cut off, or you have additional. So this make your life, the designer, the hardware engineer, the life is miserable, because they need to make this one
Precise.
like this, so perfect that it's impossible. So okay, I'll give you a little, so it will be like this. I'll give you something like this. There's a gap between this. Yeah, they can do this, but their low pass filter need to be like this. So they need to use a lot of orders. For example, butterworth filters maybe like 10, 20 orders make the circuit is very lot of trouble. So they want life easier too. So what they want is you make this one to be far away. Then they can use a filter like this. It's just the RC circuit or RC low pass filter, just a piece of cake. They just use two several elements they can make this because they are very far away, separate.
So will they ever be equal?
What?
Like the middle one, you said they equal. You can't use a low pass filter.
They need to have this exact copy without any other information. So they need to separate this. If this one is very close to this one, you need extra effort to separate this. If they are far away, then that's easy, right? So for example, if I want to separate this part and this part, that's easy. I just draw a line in the middle, then you separate. But if you two set together, if I want to separate, I need to be very careful because I will hurt you or hurt you. So I need to be very careful right in the middle to separate this. You make my life task very, very difficult.
So what device you use to split the two?
Low pass.
Low pass filter, yes.
Why does it matter if we can't hear the higher frequency?
The high frequency, this is noise, this one, because we don't want the high frequency. This is the information, that is what we want, exactly the same thing. If you have high frequency added to here, so your spectrum will look like
So low pass blocking out.
what you have will look like this. See, this one is not exactly this one. So you are going to have distortion. The music you hear here is not exactly the same thing. It has not garbage noise inside. All the voice is also distorted.
I was saying, so the low pass block out all the other stuff.
Yes, the low pass will cut off the high frequencies. So you want to choose this omega C is a little bit larger usually, for example, like 20 times or 100 times larger than this one. So you can make this filter design much easier. Okay, any questions? It's good. So now you can see, no matter you design all this part or that part, you need to need to consider for a team. So here you save time, you save energy, you save money, but you make others spend more money. So that's a system, right? You work together. Okay. Next one, we are going to do how to implement this in the lab or in real life. For example, all these are on the board, on a piece of paper. It looks like good, but how to do this? We already mentioned it's easy, right? You use a multiplier. So what is a multiplier? Not your calculator, right? Your calculator can only 3 times 5 equals 15. This one is time domain signal. You have continuous signal here, how to multiply this one. Or in the lab, yes, we have this module called multipliers. You have 2 input and 1 output, as easy as your calculator. But what is inside? How, if you want to design a senior project or any later time design project, you cannot use that one, you cannot use your calculator. So how to do this? Okay, so that is what we are going to discuss. But the idea is how to implement your amplifier. Right? So from now, we say amplifier is a modulator. Is this true? We always mention this is modulation, right? And we say, okay, we imply this is multiplier. So multiplier is a modulator, yes? Yes, right? Multiplier is a demodulator, yes? Yes. So in the labs, if it's there's no modulator here, there's no demodulator here, right? They labeled as multiplier, multiplier, multiplier. You just choose any one you want, yes?
So this is how you modulate and demodulate FM, right?
AM.
AM.
AM. So we only discussed the A at the very beginning, said A times the cosine, that's the A. FM will be discussed like 3 times later, right? Okay, so now I will ask you how do you know to implement a multiplier?
You got 2 different signals that you want to combine.
Yeah, yes. How to implement that hardware circuit? Anyone knows?
Even with your oscillator?
Oscillator can do a multiplier? How?
You need two amplifiers?
Two amplifier. Alright. So the first one we know amplifier. That is good. Alright. The first one is amplifier. Amplifier means the output equals the input multiplied by gain, right? So A. Right? That is the output equals input multiplied by the gain of the amplifier. Right? And now this gain is not a constant. If it's constant, it won't work. Right? So actually, this one is this gain will be equals this beta times the output resistance, then times the input signal. Are you familiar with this formulation? That is in linear amplifier. If you take 311 or something, you should know this, right? So the gain equals the negative beta times the out. So that is the gain. All right. So this is one signal. This is the input. We can use your MT here, and this R is a constant. Right? And we can control this beta. For example, if you control this beta with the omega CT, then what's this? It's an amplifier. Multiply, right? V equals this times this. So that's the first method. The second one is, we know we have a logarithmic amplifier, right? We discussed this before. Operational amplifiers, right? Yes. So that means the output equals the log of the input. Right? So the output equals the log of the input. What we do is, for example, now we want to, this is what we want. We want y equals x1 times x2. This is the multiplier. That's what we want. But if we have this logarithmic amplifier, so I will do this, y equals e, and so first one, I implement this with the log x1. I implement this with the log x2. You give me x1, I take the log. You use this logarithmic amplifier. Then this one, I take also the log. Then we'll add this together. Use the adder, not multiply, because we want to implement the amplifier. So we use the adder, this one. Once we get this one, we use an anti-log. Then we use an anti-log, log, anti-log. Then we get this one. So basically, the diagram will be, you have x1 here, you take this log, you have x2 here, and you take this log, and these two add up together, then you use an amplifier which is an anti-log. So that is log -1. Then you get x, here is x1 times x2. So that's the second method. You have x1, MT, you take the log. This is x2, cosine function, you take the log, then you add together, then you use anti-log, you get the multiplication of these two. Questions? Right? So anyway, these two are actually only one way, so this is multiply, right? So we said this is 1, this is 2, but we call this is a big one, right? Now, big 2. Big 2 is, we are going to use nonlinear device. Nonlinear device means y equals ax, that is a linear device, right? So the output voltage, when we discuss circuit, linear amplifier. So V out equals a constant times V in, so that A is constant. So that's a linear circuit. Linear, if you draw this, this is a straight line, right? Y equals ax, this is the slope. For nonlinear device, that means we need to have a quadratic term. that's bx squared, like in a diode, or in a transistor, high order approximation. So we have a square here. Suppose we have a circuit look like this, then how to do this? The circuit will be look like this. You have MT here, and this is the cosine omega CT. Okay. Before we do the circuit, we do the math first. So I will make x1 equals MT plus cosine omega CT. These two signals add up together. Keep in mind, what we are looking for, what we are doing. Don't get lost. What we are doing. We try to do this, multiply this, right? We try to do the modulation. We try to this one, multiply this. Everybody is clear here? That is all these things, we try to multiply this with this one. That is our task. But first you do this plus. That's easy, right? Okay, then you have the second signal. You use MT. So that one is minus this one. Cosine omega CT minus MT. Then cosine omega CT plus MT. One is cosine minus MT. One is cosine plus MT. You make these two signals. Right, now you plug this signal into here. Also here. You get Y1. Then you plug this signal here also into this as the input. You get Y2. So Y1 will be equals I just copy the math here. Omega plus M and plus B cosine plus M squared, and Y2 will be A cosine minus M plus B cosine minus M squared. You just plug this into here, you get Y1. And you plug this into here, you get Y2. Alright, now we need to subtract Y2 from Y1. So Y1 minus Y2, these two subtract. So you are going to get 2AMT then plus 4BMT times cosine omega CT. That's just math. We implement this, plug into here, you get Y1. We implement this, you plug into here, you get Y2. Then we subtract Y2 from Y1. That is what we have. Okay, now let's recall what we want.
To multiply.
We want the multiplication M times cosine. Do we have that?
Yeah.
Yes, where? This one, right? See, we have this part. After all these additions, nonlinear device, okay, we have this term. But this one is not what we want. We don't want this one. This is what we want. So we need to use a filter to cut off this. What frequency is this? High or low? This is A constant. This is MT. So that is a low pass, right? 20 Hertz at most. This one, shifted version. So this is high frequency. So this is what we want, this one is not. So how to do this? Use a high pass filter. So we use a high pass filter. We cut off the low frequency, we get this. That's all. But in real life, we do not actually use a high pass filter. Instead, we use a band pass filter because we don't want any high frequency noise. So we use a band pass filter. That is practice. So theoretically, we use a high pass filter. That's good. Questions? All right. So that is the theory. How to implement this? I ask you to go to the lab to do this. How are you going to make this? What we do is we have a MT, we have cosine omega CT here. Now we have adder, right? This and this add up together, so we get MA. This is XT. And we pass a nonlinear device, we get Y1. And here, this signal and this signal, we add up together. Remember, this one here is minus, this is plus, this one is plus, this one is minus, this minus this. Both are plus over here. And we get X1, we just follow this, right? And this one, and also we pass through the nonlinear device. Okay, that's part, we have Y2 here. Right? Now we need to use an adder here again. And we use Y1 minus Y2. So this one is positive, and this one here is negative. Then we get this part. And we need to use a band pass filter. Then we get 4B times MT times cosine omega CT. Right? That's it. That is what you need to do in the lab to implement this. You give me these two signals. I have adder here, nonlinear device here, and adder here. Okay, band pass filter. Now this one is your output. When you buy the amplifiers, okay, so you said this one here are the just box like this one. You cannot see this. You need to design this part. What we can see here is one button, input 1, input 2, output here. That's all. Any questions on this? It's good? Okay, now we have the last one. That's very, very interesting also. In the first homework, remember, I let you to verify that any periodic signal can be represented by a sum of cosine and sine functions, right? The example I give you is the impulse train. Let you to implement this. I hope everybody already done that. The key here is, suppose we have the next one, third method. We suppose this periodic function, periodic signal, right? Rectangle pulse train or triangle signals, no matter what. And this one will be implemented by the sum of all Cn times the cosine n omega Ct plus some initial phase. Right? The periodic signal can be represented by the summation of all these cosine and sine functions. We know that, right? Okay, so now what we do is we multiply this mt with this phi t. Let's see what we have. Okay, let me ask you again. What do you want? What we are doing? No. What we are doing all these things.
Trying to get them signals.
We try to do mt times cosine, right? That's what we want. Always keep in mind, right? So what I do is you give me any periodic signal first, right? Mathematically, I can write this one as this. You already know that, right? And see, I will multiply the mt with your periodic signal. Let's see what we have. So that one will be a sigma Cn mt then times the cosine. I'll copy all this part plus this one. Right? Now I write this one term by term. So this one is C0 mt plus C1 mt times cosine omega Ct plus C2 mt times cosine 2 omega Ct plus theta 0 and here plus zeta 0 or something, and infinite terms.
Oh, okay.
Right? And from 0 to infinite terms. Right? Again, what we are looking for?
In times cosine.
Do we have that?
Yeah.
Yes, here. Right? This one? No. This one is what we want. And all these are high frequencies. Low frequency, this one is what we want, and we have even a lot of copies of at high frequencies. We have more than enough. And that's the low frequency. This one is exactly what we want, and this one is even higher. Let me draw this. This is the original. This is what we want. And we even have more. And infinite terms. This is what we want. So how we do have this one in here. So how do we get this? Band pass filter. Right? So we use band pass filter. Get this one. That is math, right? Mathematically, yes. Now the case, how to do this? We do not actually do this multiplier. If you have multiplier, why you want to bother all these things, right? You just multiply these two together, that's all. All right. Good news is, for example, this phi is this. That's why in homework I let you test this one. Periodic is impulse train. So this one times this. What does that mean physically? Your MT multiplied by this signal. So this is 1, this is 0, this is 1, 0. And what does that mean? That means you have this MT here. You have a switch here, like this. You multiply by 1, you get MT, right? This signal MT multiplied by this signal. When you multiply by 1, you get MT. When you multiply 0, you get nothing. Yes or no? So you multiply by this 1, 0, 1, 0, 1, 0 means you have switch here. You make this on, off, on, off, on, off. Yes or no? Okay, now this is done.
Sounds about right.
This is done. You give me your baseband signal. I use a switch. I turn this on, off, on, off. All right? Open, close, open, close. And this part, you need to have a band pass filter. And then you get the modulated signal. That's easy, right? So actually, we do not need to use any multiplier. I only need to use a switch. That is what we have here. My voice is continuous, but you multiply on, off, on, off, on, off. You hear this. Then you pass this thing through a band pass filter, you get the modulated signal. Questions? No questions, right? Everything's good?
Yeah.
Like we have a switch here, right? If you have a signal, you just on, off, on. Oh, no, okay. Too slow, right? On, off, on, off. Okay, that is the. You use this on, off. Then pass filter, band pass filter, you get the modulated signal. Okay, so here, what is this frequency? We want this frequency to be high. This on, off, how can you do this very fast? Like in each second, can you do this like 1 million times? 1 megahertz. Can you do this? Anyone can do this?
No.
Can you do this on, off in each second you do this 1 million times? No way, right? At most 10 times. I tried, I can do 11 times. You can do 10. Okay, so that means the frequency can only equal like 10 hertz. Okay, that is too low. My voice is 20K. There's no way. So how are you going to implement this switch with a higher frequency? Anyone? We need to use this high-speed switch. You are electrical engineering. E. So, what switch do you suggest? electronic switch, right? Electronic switch.
No,
Yes or no?
Yeah.
Yes. What is electronic switch? Can you tell me what? Don't say you buy from Amazon, right? That doesn't count. You need to implement, make one for me. The diode rectifier is one, right?
Right.
No, that one is in the lecture notes. So that is right. The first one is like this one. I will implement one for you. The time you buy this from me, right? We are going to use the electronic switch, to save your life. Don't make you to do this. So the first one is called a diode switch, a diode bridge. Circuit modulator, or called switching, switching modulation. How to do this? Look. Right? This is a diode bridge. We have 4 connected like this. And we connect this point A, terminal A and B. This is C and D. What we put between C and D is this cosine function, your cosine omega CT. This one is a cosine omega CT. Cosine omega CT is a sinusoid function. So we have positive, we have negative, right? So when it's positive, that means this C is higher than D. The potential at C is higher than D. If C is higher than D, what does that mean? If this potential here is higher than D by at least, for example, 1.4 volt, high enough, this one will conduct, right? This one will conduct. So that means this one is a straight line. Yes? And this one is also a straight line. Hello? Yes? See, yes?
Yes.
Yes, alright? So that means A and B are short circuit. So A and B are connected if this part is higher than this one, high enough. So A and B is like this. So A and B. Good? How about if C is lower than D? Because this one is a sinusoid function like this. Okay, higher, lower. If this one is lower than this half cycle, this one is higher. This one will close, right? This one will close too. So that means between A and B, that is open. Like this. Now this one is fast. No matter how fast, your cosine omega CT is on, off, on. So we can say close, open, close, open, close, open. So that is electronic switch. Right? So now, how to implement this one? Yeah, this is the switch. So I will move A to here like this. You connect this point to A, you connect this point to B. Here, here. And in between, we have this diode bridge. So if cosine omega C is higher at C than D, then that one is closed. It's lower, then it is off. Yes, this one is on. This one is open. So by this one, control this speed here. This one will on and off. That's all. Make sense? Do not make sense? Okay. So I can use this way, right? This method. This is one way. Another way is this is MT here. I will connect like this. This is what we, this is A, this is B. Can we do this? This one is in series switch. This one is in parallel.
Right.
When this one is closed, that means this is 1. So we have a signal. When this is closed, so this one is closed, that means this is short. So we don't have signal here. Right? When this one is open, that means that we have 0 here. When this is open, we are going to have signal here. So this one is just the opposite to this one. This is 1, 0, 1, 0. This one will be a 0, 1, 0, 1. But anyway, switch. So you can connect like this, or you can connect like this. Both work. Questions?
What the bottom two names of those?
Switching oscillator, switching modulator. Use this one, switching on, off, on, off.
So what diodes located in the bottom two?
What diode? We connect this one. We always use this bridge.
Oh,
This
okay.
point is B, this is A. So you need to connect the A to this point. This B is here. So you shift, you move all this bridge to here.
Okay.
And or you move to here, but B is here, A is here. You connect like this.
Okay.
If we draw the time signal, suppose your MT looks like this. Suppose your MT looks like this. And this is your MT. Then you pass through this 1, 0, 1, 0. What you have is we are going to have we are going to have this part. This is 1. And here we have nothing. And we have 1 here, we have nothing. We have 1 here, we have nothing. We have 1 here, we have nothing. So the signal we have actually is looks like this, 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 this. That is what we have. 1, 0, 1, 0. Pause, stop, pause, stop, pause, stop. And we have some all this like this. So you can see we have a DC component inside,
Did you
right?
accidentally summon me?
We have a DC component inside, right? That means DC component is not what we want, right? So what we want is we use a 4-wave rectifier, right? Means we can pass both parts. This one is called a half wave. Even better, we can use a 4-wave rectifier. And we are going to double the efficiency. Right? The 4-wave rectifier, you know how to do this, right? You need to use a transformer, use the central tab, and to do that. Right? So on the slide, you can see the waveform different.